left early might not have known it, and I'll just want to see if anybody else has any other comments. The other thing is, I'd really like to thank the people who supported us at Jet Energy, and Dave Nagel and Steve Katinsky and Nathan Cohen, who've helped put this together. I want to thank Jeremy Rice and Barry Simon and Ruby Carrot, who left, because they are a big reason that you're here too, that you know what's going on. So why don't we go now to talk about patents. There was a question yesterday about the difficulty of obtaining patents from the U.S. Patent Office as opposed to perhaps other countries. And Brian? Where'd Brian go? Oh, maybe we'll come back to this.
You wait for a coffee, you'll be right back.
Okay, we'll do.
Standing by if there's somebody that. We can cover it later, Mitchell. If
we will.
Again.
We will.
Sure.
It's a topic.
Everyone's hot to get on with the real stuff.
It's also a topic that probably won't go away too fast.
That's true.
So we'll start off with Peter Hagelstein, who will talk about anomalies associated with fracture experiments. There's the laser. If you want that. Do you want this too?
No.
Thank you.
Okay, let's get started. So on Friday, I talked a little bit about experimentation and emission of collimated X-rays. And yesterday, I talked a little bit about a model that we had developed to deal with it. Subsequently, some of my friends asked me some questions. They said, in your model, you got this foil moving, you got some mercury atoms on it, and they're just moving back and forth. How does that exchange any energy? And I thought, that kind of picture wouldn't exchange any energy. And I said, what happens is when a nucleus moves, if it's got to do the Lorentz contraction and spin realignment, that you get coupling to internal nuclear degrees of freedom. So instead of thinking about a piece of copper that's just vibrating mindlessly, which is a sort of a normal condensed matter kind of picture with the mercury atoms on it, when the copper is moving, the copper nuclei in it also have to respect Lorentz and have to rearrange themselves. So the vibrations of the copper are talking to the internal nuclear degrees of freedom in the copper. And then when you put the mercury on the surface, it's not that the mercury is just moving because the surface is there. The mercury is now sort of doing the same thing when the copper nuclei are doing the same thing. And that gives you an indirect way for the mercury nuclei to talk to the copper nuclei, and you get mixing of the degrees of freedom of the vibrational and the nuclear degrees of freedom. So if you like, that's underlying, that kind of idea is underlying where we're going to go here. So I'm interested today in fracture experiments. There's a group at Torino involving Carpentieri, Cardoni, Lacedonia, who have been doing some astonishing experiments. I'll talk about them very briefly. They've extended their conjectures to include geologic implications. And that leads us to, if any of it happens to be right, and we've talked a little bit about transmutation the last couple of days, so I wanted to talk a little bit about how it might work theoretically. So that's where we're going. So the beginnings of this is a little bit of sort of a review of experiments done in Italy. Not just experiments done in Italy. There's a whole field of fracture. So again, as a way of motivation, if you believe that having vibrations around can make something happen by inverse fractionation or upconversion, then one thing you might be interested in is an experiment that maximizes the vibrations. So for example, if you have a piece of stone, for example, and you apply a great deal of pressure, if you apply enough pressure, you can cause the stone to break. And when it breaks, it's a sudden kind of event, and you get catastrophic failure. And what happens is if you've got transducers, strain gauge, piezo transducer pickups, you can measure acoustic energy. And this is time in microseconds, so 10, 20, 30, 40 microseconds. And you get these very large amplitude vibrations that follows fracture. And you might say, aha, so from this picture I learned that fractures produce vibrations in the megahertz region. Well, probably fractures produce large amplitude vibrations all the way up to terahertz. It's just that the higher frequency that you go, the faster the damping is. So if you're a macroscopic distance away, all the high frequency stuff is going to be gone. So when you're measuring a distance away, you're limited to the frequencies that can actually propagate there, which tends to be megahertz. So in the Carpentier experiments, they measure the acoustic emissions. By counting the number of acoustic emissions that occur, you can match the theoretical models which tell you something about the fractal dimension associated with the fracture plane. And it's just not the Torino group that's doing it. There's a large literature on acoustic emissions that goes back forever. This has been studied for quite a long time. In some of the literature I've seen, people measure the acoustic emissions to do a radar of sorts to go back and figure out where, or sonar to figure out where the fracture occurred. There's also electromagnetic emission. So the Torino group says they see electromagnetic emission. I thought, cool, they see electromagnetic emission, that's anomaly. We go back to the literature and everybody measures electromagnetic emission. In fact, so AE is acoustic emission for different sensors. This is electromagnetic emission. And the electromagnetic emission shows up faster. Why should it show up faster? Well, the sound speed of acoustic waves is slow. Electromagnetic waves go really fast. So when the fracture happens, the electromagnetic emission occurs, and at light speed you get to the detector. And you can use that for timing to figure out how long it takes for the other sensors, and you can use that as a way of doing your sonar. So the question is, so there's a precursor electromagnetic signal. The EM signal has been studied, and it's been concluded that it's a result of the fracture event itself, and not due to subsequent physics that's going on when the waves are propagating all over the place. I was interested in this electromagnetic emission because if you study it, you can figure out, I mean, you know that electromagnetic emission is a result of charge moving around. So if you believe that there's lots of charge moving around causing fission events or nuclear events or so, you have information directly that you can measure to place limits on or make models up for the charge emission. Now, it turns out that, again, if you poke around in the literature, you find that people have already studied this. It's been studied for decades. So here's an experiment where people take a sample of ice, they do the compression thing, they get a fracture, and they measure the electromagnetic emission. So the electromagnetic emission is measured as the shaky data here, and it's compared with a dotted line, which is theory. And the theory in this case is interesting, because I would have figured you get a fracture plane to go and separate, so you've separated charge, you're going to get acceleration across the air gap. And it turns out that the model that's used that gets such good results here isn't that at all. In fact, the model says that when you fracture, you get a conduction pathway along the plane that just fractured. So the calculation, there's a finite difference simulation that was done, a fairly sophisticated one. So you get the fracture, you get the charge separation, and the current follows the current path around where the fracture occurs. So if it goes like this, then it goes in, and then comes back out. And that kind of model ends up giving really good agreement with the observed electromagnetic field. So the primary effect is sort of more normal conduction and not super fast acceleration of very large numbers of high energy charges, which at this point will become important a little bit later on. So how does this relate to anything cold fusion-ish? Well, associated with the fracture, they see neutrons. So for example, here's the load building up. So I have a piece of stone, and they're compressing, 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 and then all of a sudden there's a catastrophic failure, there's a fracture, and here's the neutron emission being observed, and all of a sudden when the fracture occurs, it blips up and it comes back down. So as you can imagine, anyone that says you have an anomaly that even smells like cold fusion's going on, the critics pop up and they say, well, you know what's going on is your neutron detector's getting hit by these sonic waves from the fracture, and it's ringing and rattling, and you got noise. So, and a million other critics. So the neutrons are time correlated with a catastrophic failure. They did it first with the helium-3 detector, and the critics said, well, your helium-3 detector is going to be influenced, so then they got bubble detectors. And the bubble detectors aren't sensitive to the electromagnetic emissions, but I was there, I visited Torino to give a talk, and they had a demonstration in the lab, so I got to see this thing fracture. And they had these bubble detectors around. So you're looking at the bubble detectors, clear as anything. Fracture, bubble detectors over here. I'm not being blown back by any sonic waves. And the bubble detector's dark. It's a gazillion bubbles in there. And I'm thinking, there's so many neutrons to make the bubble detector. What happened to me? Am I a bubble detector? The effect is reproducible. According to the Torino group in the literature, the signal is large. So large. 10 times background or so, which in our field my friend Mike McCubry has these conversations, and so he says, well, we saw neutrons 10 times background, this is a very large signal. Mike chuckles and harumphs and says, sorry, 10 times background is not large in this field. And you can see it and you think maybe it's real, but not large. And in this case, it's correlated with iron in the sample. So if they have stones that don't have iron in it, they don't get neutrons. The stones that do have iron in it, they do get neutrons. There's additionally a recent paper where they've tried to look for alpha emission. And if you're going to try to detect alphas, there's various detectors that are specific for alphas, and you could put foils and distinguish and so forth. Here we've got a scintillator, we've got a Geiger counter, and we've got a couple of peaks above background. We've got some counts that have something to do with the fractures, and they tend not to get counts when you're not doing the cycling to get fractures. So from my perspective, this is still preliminary. I would actually like to see a real diagnostic and see a demonstration, particle identification done properly. Nevertheless, it's suggesting that maybe there's a signal to look for. They see elemental anomalies, and the elemental anomalies is what it is that is attracting my attention mostly, and the reason I'm up here talking to you. So in the case of the elemental anomalies, here's iron concentration, and here is the iron concentration in this particular sample on the external surface. So the external surface has not experienced a fracture. Here's the iron concentration. So you've had a fracture, you've had a catastrophic fracture. Now you have a new surface you can look at. So they analyze the new surface, and here's the iron concentration in the new surface. And there's less iron there. So you can say, well, what happened is your fracture occurred in places that were chemically different, so it's weaker. On the other hand, this kind of effect is reproducible. In addition, here, so this is the aluminum on the external surface, and this is the aluminum at the fracture. And so what Carpentieri, Cardone, and collaborators have noticed consistently is iron goes down, aluminum goes up. If you don't have any iron, you don't get the aluminum showing up. And not in this experiment, but in other experiments, they've got the amount of iron going down seems to be half as much as the aluminum going up. So this is an elemental anomaly, and this has given rise to the conjecture that iron 56 is, I'm not sure what the appropriate phrase is, being disintegrated, being fissed, a fracture-induced fission mechanism to 2 aluminum and 2 neutrons. So the idea is that you start out with iron, you lose iron, you see aluminum, and if you look at the nucleon part of it, you've got 2 neutrons to spare. They measure a few neutrons, and so that's good enough to propose a formula. There are issues. So, as I've said, in some experiments there'll be very little aluminum there initially, and then the initial aluminum that's observed will be correlated with the new fractures. Reduction of iron down in amounts that are half the amount the aluminum goes up, neutron emission. From my perspective, seems like if you're going to be measuring, this should be aluminum. If you're measuring new aluminum, to be able to see it, there has to be a lot there. The number of neutrons that they're measuring is a very tiny number, so I don't see how the new aluminum could possibly be balanced to the number of neutrons that are produced. But it's a question, and it's not been addressed quantitatively. Now, Carpentieri and company are connecting this with geological issues, and the geological issues work sort of like this: that the big iron mines are located in these locations, and they're located in regions away from fault plains, away from fracture plains. Whereas the aluminum mines, the aluminum mines are located in places where there are fracture plains. So the thinking is that you start out with iron uniformly distributed, and then in places where there's been fractures, you turn the iron into aluminum. I hear chuckling, and the first time I saw this, I chuckled myself. But Carpentieri is pretty committed to this.
I don't really like the idea.
So the conjecture is that maybe this effect that they're seeing in the stone fracture experiments can actually begin to account for the occurrence of aluminum on the Earth's crust. So here's for example, this is billions of years ago. They've got ways to figure, and they can look at parts of the Earth's crust that date from different archaeological or geological periods. And what Carpentieri's done is he's put together a plot of the abundances of different elements over the geological record. And the argument that he's making here is you started out with iron and aluminum in these ratios, and then you've changed to these ratios. So the basic argument, you're losing iron, the aluminum's going up. And in this particular case, it looks like you're losing a lot more iron than you're gaining aluminum. But the argument, once again, is that iron being converted into aluminum is something that he's arguing there might be evidence for in the geological record. However, let us now return back to the literature and known laws of physics and so forth. So disintegration of iron-56 is, of course, well studied in the nuclear literature. It takes a lot of energy, as I will show shortly. It's sort of easy if you've got 20 or 30 MeV of energy in your incident particle to get proton-neutron ionization or alpha ejection. If you put in more energy, you tend to see decay. You make this compound hot Bohr state, and you can get everything decaying in proportional to the tunneling probability and the associated statistical weights. In the nuclear literature, there's by now standard theoretical models and codes that can be used to calculate distributions, probabilities, and everything compared with the experiment. And you can see in the literature data plots from these codes, and they overlap beautifully sort of over all ranges for all materials, and things work really well. The bottom line is, based on what we know about nuclear physics, we would not expect this iron going to 2 aluminum, 2 neutrons to be a particularly high likelihood event. But let's go and let's draw some pictures and look at some data and think about it. So one possibility is you come in with a particle, maybe a gamma, maybe electron, maybe a proton, and this guy is going to interact with one of the nucleons and basically kick it out. That's sort of the simplest view, and that occurs at low energy as a dominant process in many nuclei. Another thing that can happen is the particle coming in can interact with perhaps first one nucleon, but then the one nucleon hits its neighbor nucleon, which hits another neighbor nucleon, and you get a thermalization, so the energy that comes in is spread to everybody. So you get a compound state, which is a very high temperature, and then the compound state just sheds energy as it evaporates, if you like, as best it can to cool itself. So you end up with different fragments coming off, more mass, less mass, neutrons, alphas, all kinds of things. So now, there's been studies done in early years and published on particular things. Now, iron-56 has not been the largest studied candidate in these early studies, but it has been studied. But here's an example for nickel-58. So here's the response for A, and I look at A, and A says come in with a gamma. So this is photodisintegration, come out with a proton. So that's the biggest thing that happens here or that's listed. Here's gamma neutron, so that's B. So proton more, neutron less, but centered at a response sort of near 19 MeV. So this big response is called the giant dipole response of a nuclei. And different nuclei have giant dipole responses, reasonably sharp, located generally between 15 and 30 MeV. So now we can see some disintegration. This is photodisintegration. Electron disintegration works very similarly. So I'm thinking giant dipole resonance dominates cross sections 20-30 MeV, which is the source of my comment to Pam of what this response, the 10 to 15 MeV alphas, the fast neutrons, fast protons, I think is a result of the existence of the giant dipole resonance. So you get a little bit of stuff coming out, but we're not taking iron or things near iron and splitting it in half. So the idea is that we need to hit it harder to get bigger fragments out. So let's come back, let's use a bigger hammer. So instead of coming with 10 or 20 MeV, this time I'm going to come in with 320 MeV X-rays, Bremsstrahlung X-rays. In this case, it's arsenic. So I'm starting out with arsenic, and I've got 320 MeV coming in, and now I'm able to split it up into more stuff. And so here's some of the more stuff that I can split it into. And if you look, the stuff nearer to gallium, so mass to 75, or arsenic mass to 75, if I've got just a few nuclear masses coming off, it's got pretty high probability. If I've got 15 to 20, if I'm having oxygen come off, the probability goes down by more than an order of magnitude. So even if I come in with more energy, I'm still not getting a 50-50 split. So Still not hard enough. So I can do experiments of higher energy. I can get O16, but it's lower probability than lithium-6 coming off. So what I'm finding is that it's hard to produce fission with roughly equal mass daughters at only 320 MeV. Need more energy. Bigger hammer. So hit the thing harder. I'm determined to break my iron nucleus. Now there's an issue that when you start hitting the nuclei harder, you get other things to come out. It turns out if you hit a proton hard enough, you can get some pions to come out. Say, what pions? Two quarks bound together, they come off. It turns out the cross-section for pion emission in chromium here is more than an order of magnitude higher than for proton ejection once you're above the pion threshold. So if you're going to really break apart iron or any other nucleus by using a hammer and doing it energetically, you're going to get pion signals out, which would be a real easy way to prove that you've got really energetic particles present. Okay, so here we're coming in with a GeV, and we're blasting natural copper, and we get nickel, cobalt, iron, we got all this stuff. If you want to get, here's magnesium, and this is sort of a little bit like iron going to aluminum. So, you know, it's an analog, but we see we're down by like order of magnitude and a half in probability. So we're seeing that you can break the nucleus near iron in half. It takes on the order of a GeV to do it, but when you do it, you get everything else, and it's pet giraffe showing up. So we see that fission can be done, but it's non-selective. You get everything coming out. So here's an experiment done specifically with iron. And this time we've got an even bigger hammer. So here's 100 MeV, a GeV, 10 GeV, more than 10 GeV if we need it. So iron, here's manganese, here's chromium. So to go from iron to manganese, you come off with 1. To go to chromium, you come off with 2 protons. There's vanadium, more manganese, scandium, iron 52. So here's a sodium. So presumably aluminum might be sort of in this region. So it's down by orders of magnitude in iron. So once again, we're seeing in the nuclear data, we can break iron apart. It takes a heck of a lot of energy to do it. And you're above the pion threshold to get any finite probability to do it. But you get everything else out as well. So the experiments in the relevant energy regime, electrodisintegration, photodisintegration is similar. We can break it. Splitting of iron into aluminum-2 neutrons is definitely low probability. And this is definitely not a qualitative match to the observations of the Torino group, at least according to me. Transmutation has been talked about a fair amount yesterday and the day before, and will be talked about some more. I'm looking at Professor Iwa, or Dr. Iwamura, and I'm thinking fission here, not adding mass to it. But so we've got elemental anomalies reported with hot spots in palladium deuteride. We've got Miley's drew our attention early on in this country to transmutation from the nickel-hydrogen studies. Piantelli's experiments show elemental anomalies, and there are a great many more. If I were to be honest about this list, this would go on for 4 or 5 slides. Here's an example in a Piantelli experiments. It's hydrogen gas nickel bar, and the nickel beforehand looks like this, where here's peak for nickel, the K alpha, the L of nickel, and then after they run and produce excess heat for a while, then on the surface they get nickel and calcium, potassium, chlorine. They get the rogues gallery of stuff, and this is not so different from other things that we've seen earlier. Here's a surface scan from a different experiment. So we've got nickel going down, we've got manganese going up, and if you like, the amount of manganese in this case is more than the amount of nickel. So it's a lot. Let's see, the concentrations, nickel is down at 5%, manganese is 15%, 5, 15 adds up to 20. There's got to be some other stuff on there. Oh yeah, and here's some of the other stuff. So here's some chromium, here's some iron, 70%. So it's sort of as if in this experiment the nickel is being disintegrated, if you like, down to iron and chromium, which sort of means you're going to get protons and alphas off. And it turns out this bar continues to do its thing when they take it out for 5 or 10 minutes. And they had a cloud chamber nearby, so they stuck it in a cloud chamber. And they see massive amounts of this energetic stuff coming out. They got protons and alphas. And they took pictures of it, and in some of their pictures and so forth, the number of tracks is frighteningly large. So thinking about it, so elemental anomalies, fractures, there's elemental anomalies claimed now for these fracture experiments. And I'd like to see more studies and different kinds of measurements to be really sure that it's a real effect, but at the moment it's looking interesting. We have elemental anomalies in LENR experiments, in some cases with correlation excess heat production, namely hot spots hot, get melting, you get elemental anomalies, so heat production, elemental anomalies, Piantelli experiment, excess heat, surface, elemental anomalies. So I'm kind of thinking, got fractionation, inverse fractionation model in the SRI experiment, in the Carbut experiment, Vysotsky and Kornilova. So we've got a way to have energy going in. So I'm kind of thinking, I'm heading in the direction of thinking, can I have a lattice-induced fission effect? So I mentioned this the other day. Now, I'm of course not the first one to come along and think about fission in connection with LENR experiments. In fact, there's earlier work. So far, the earliest reasonably serious model that I've seen so far is actually by Mizuno. It's a respectable calculation in this paper. And so Mizuno was trying to account for elemental anomalies they've seen in palladium in experiments with hydrogen. And the proposal was that a large number of lower energy photons was occurring to get you up to a compound state, and then you'd fiss. Mizuno hooked up with Takahashi and some colleagues, and they had a publication of this kind of model. And subsequently, there's many publications and calculations of all kinds of fission events from this kind of model. We heard from Cook, who has this lattice nuclear model, is calculating fission probabilities. I think Heinrich Hora also, I should have had him on here as well. Heinrich Hora's and George has studied a model that they modeled fission. And recently, Whittam and Jim Swain and Srivastava have a model where they basically propose that very energetic electrons near 200 MeV are coming in and causing fission of iron in the Torino group experiment. So the models are clear enough. You can do calculation, compare against experiment. And here's one example. And the agreement's sufficiently good that you start thinking that, well, maybe these conventional fission models have some kind of relationship to the observed transmutation. Here's another example. This is Cook's model against some transmutation data. There are many such plots. I could keep presenting them for the rest of the hour, but the idea is that that the models are sort of relevant because they sort of describe the spread that you see and get something, some information with respect to relative probabilities of different masses. So from our early discussion, we say we need lots and lots and lots of energy to induce a fission event kinetically. The different energetic disintegrations are not selective at all. With these kinds of mechanisms and all the theories proposed in LNR so far, we'd expect radioactive products to show up, expect significant gamma emission, which is not seen, and not only even, but especially in the LNR models proposed so far. Now, in my view, fission, if it's occurring in these fracture experiments, is selective. And fission in the LENR experiments, if real, and I've got the if real, my disclaimer, this is MIT, so I don't want the physicists to come in and throw me out the window, so you have to be mealy-mouthed about it. But the LENR transmutations, in my view, I think are real, but they show very high degree of selectivity. And I'm going to point out that fission's incoherent process is distinctly non-selective. So I think an incoherent fission mechanism just is not a candidate out of the box and is never going to work and is not going to be able to be modified ever to work. So I conclude that in incoherent physics, I'm going to cross that off of my list of models to consider. So I've been talking for ages, since the last millennium, about coherent mechanisms for fusion, and propose a coherent mechanism for nuclear excitation for car-boot SRI experiment. We've got a model now to describe the energy exchange. In order to have there be a coherent fission event, basically all we need is pathways involving long-lived states that get to states, final states that are long-lived with fission decay pathways. Now, the conjecture has been made and been published and discussed also at ICCF 17 briefly. So the question is how might it happen? So in this case, instead of conjecturing that this might happen, that might happen, let's go to studies that have been done that have been relevant. So in the mass 60 regime, there's a nuclear physicist, Rudolph, with a very large group and more than a decade's worth of studies of this that have been studying collisions. So you've got an energetic nucleus coming in, you've got a collision, and then you're producing high spin states of things like nickel and copper, so things near iron. And what happens is the more you start spinning the thing, so here's the angular momentum, so spin, 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 the more the energy goes up. You spin something that's small, you get some energy and it goes up. Now, the faster you spin it, the more you get up, you can imagine that it gives you some centripetal forces. So it tends to want to pull things apart, makes the thing non-spherical. So for example, here is an example from 2002 of states that they studied in copper. And what's interesting is they do the collision. So here's the states for normal copper, which is fairly close to being spherical. But when you get this high rotation, you're generating states which are beginning to be deformed. And when they get deformed, they find a band edge. And when you get to the bottom of the band edge, what's interesting is that going from here down to here somewhere ends up being forbidden because of the angular momentum issues and deformation issues. On the other hand, there's a disintegration, a fission decay, if you like. Now, not much of a diffusion of a fission event, but you get a proton coming out and you decay to nickel. Well, this is a little bit unusual. Nuclei around mass 60 do not do proton decay normally. This is not something that you see. But here it's seen in this case, and not only do you see it, but you can tell from the angular pattern that the spin states involved are high. You're spinning, you're spinning, you're spinning, you fly apart, but you still remember that you were spinning before you flew apart. So I'm thinking about this. So how do you arrange for the long-lived intermediate states? Well, at the bottom of the rotational band, it's reasonably stable. There's no gamma decay. And depending on what the decay time is for the proton decay or other fission channels, which can be long, they might be slow. So this might actually give you some states where you could march up and get a fission going. So for example, here's a more recent experiment and theory are coming together to map out some of what these bands look like. So the picture is here's a little bit like a molecular system. In a molecular system, you've got different states, and you rotate, and there's a band minimum at different places. So here's the same kind of thing in the nuclear states. So the more you spin, the more you deform. The more you deform, the more you can get minimize the energy of the products on one side and the other, you get a minimum. And these minimum tend to be pretty stable against gamma decay. They're fission unstable, but depending on the details of it, if there's a big Coulomb barrier, they're going to be very stable against fission decay with a large barrier. So you can imagine more and more and more of these things. The phonon exchange business can go up to M4 selection rule, which actually means a fair amount of angular momentum for each phonon excitation. So you can imagine a scheme here where you start with nickel, or you start with iron, or you start with palladium, or you start with some other nucleus. Phonon exchange is spin the thing up. The coherent business is going to maximize probability of the most long-lived states, because the coherent processes, they tend to not like things, states which have fast decay times. They seek out the long-lived decay states to do their business with. So you now have a pathway. You start out with a nucleus, you exchange phonon, the energy, a fair amount of energy comes in with a phonon exchange. You spin the thing up, and once you spin it up, it gets more and more deformed. And then, depending on where you end up, how much energy you give it all along, you know, it keeps on accepting energy. If you have a large amount of energy to give, it's going to keep on going until it gets as much as it can go, which is the 50-50. And then you can imagine that it would come apart with low decay time at the other end of it. So that might be a route for getting a near equal dot or FIS coherently. So the issues is from conventional nuclear physics studies, we know we have lots of bands. We have relative stability at the bottom of the bands. We got single phonon can actually exchange a fair amount of total angular momentum. Many successive coherent transitions could spin up a nucleus and make deformed states, which might give you daughters with a great deal of selectivity. So the advantage of the approach is, in my view, selective fission is impossible by any incoherent models. So this is, in my view, is the only game in town. It will connect it closely to the X-ray emission experiments. We've got a fundamental Hamiltonian. We've got the lossy spin boson model to describe inverse fractionation. And at this point, based on what we know, we can actually envision a theoretical program where we actually calculate out these states with nearly conventional nuclear models, set up the coherent calculation, try it out, see if it works, and see if we can actually demonstrate with an honest model calculation this pathway. Okay, so discussion. Now, one issue is the fracture is not, in the fracture experiment, the fracture is not so well controlled. You crush and it splits. You don't know beforehand where it's going to split. You don't have a diagnostic that's sitting here looking at the fracture plane when it's splitting. So the question is, you know, should we take the SRI experiment, go to higher frequency, transfer more energy, and try to coherently FIS nuclei? Maybe you go up to 10 or 100 gigahertz, or you go to terahertz range, and you drive and you drive and you drive and transfer the energy. And I mean, my fantasy here is that we figure out how to get lead vibrated up, FIS lead to stable channels, and we have a cold fission reactor. Kind of the opinion that that's actually what Mizuno's device that we saw yesterday was doing. And sort of like it.
You're doing that fracture experiment with your vibration. When you you have aluminum, and if you have any mercury or else, it's going to go right to the grain boundary. You're never going to have any mercury on the surface of that aluminum carbide. And in your copper one, you're going to etch those boundaries. So you have an array of fractures, which are called grain boundaries.
Right, but the SRI experiment's not working on fractures. Here the issue, there's no significant amount of mercury intended to be put in these things. It's, well, I haven't seen the elemental analysis.
You're not having mercury, but your stuff is well controlled. I mean, you're vibrating.
Okay, tell you what, let me finish. I'm just about done. And then, okay, so one issue is, can we get different end products with less energetic fractures? Alternatively, if you had a controlled version of it and you transferred less energy, could you pick and choose what endpoint channel? If you're going to have selectivity, can we get control over the selectivity? I think we should be able to. Okay. Coherent versus incoherent. So inverse fractionation provides a mechanism for coupling energy through phonon exchange. Terahertz vibrations are, of course, much more effective than gigahertz, which are much more effective than megahertz, which are much more effective, and so forth and so forth. So we've outlined how a coherent version of vibrationally induced coherent fission might work. But we'd also expect, given the inverse fractionation of the energy input, for a vibrationally induced incoherent version of the fission effect, which I think is responsible for Lipson's alphas and protons and neutrons, and for what Pam talked about the other day and Larry. I think this is how that part of it happens, and as such, I think those experiments are really important. And Pam, you'll probably try to understand why I've been asking you all those hard questions all these years, because I'm really, really interested in understanding whether this is right. So conclusions. We've got anomalous neutron, maybe alpha, and elemental anomalies in fracture experiments. Got a conjecture for a fission, lattice-induced fission reaction. Again, there are issues with this. A conjecture that this has to do with the aluminum correlation of aluminum fractures in the Earth crust, qualitatively similar to LENR experiments. Many theories around, but they're incoherent theories, so they, in my view, can't be relevant. So coherent fission mechanism to account for high-level elemental anomalies. What that means is if you get a lot of stuff, in my view, it's got to be a coherent reaction, because the coherent reactions are much, much faster than the incoherent reactions. So along those lines, I think it's relevant to the elemental anomalies reported by all kinds of folks. And if you haven't seen Diddick and Wisniewski's stuff, they run gammas through palladium deuteride. They have so much transmutation, they get a slug of other stuff popping out.
Mostly titanium.
Well, calcium oxide, all kinds of stuff. So we've proposed, there's many incoherent fission mechanisms, we're proposing now, and have proposed for years, that incoherent fission accounts for the low-level disintegration driven by inverse fractionation phonon exchange, and so forth. And that's it. Thank you.
Thank you very much for very impressive and suggestive theory for me, especially for me. Recent experiments of ours seems to be. I am thinking about the possibility of fission. So, in the case of gas rolling, we analyzed that fusion type transmutation reaction, but I should think about
actually
selective fission.
I have
very impressive, I think.
For your experiment, my favorite model is something that looks like this. I start out with a ground state nucleus, like your cesium, like your molybdenum, like. So then I go up to get an excited state where I've got a neutron promoted. Very, very near the ionization threshold. I mean, basically at the ionization threshold. And then if you like, the ultra-low Bragg neutron state. So neutron transfer, a lot like Whittam's suggesting, except that I want the energy to come from the inverse fractionation. So I promote going up. Now I can move over, and then inverse, and then fractionation to come back down. And that would give you a mass change to increase the mass. Now, there's enough evidence for that process going on, especially from your experiments, and also, Piantelli's experiments, George Miley's covers some transmutation where the mass is going up. So what I talked about in this talk is mass decreased by fission, but there's also, I'm not a believer in the fusion to make larger mass things with high Z materials. I think that's impossible because of Coulomb barrier. But ultra-low neutron transfer coupled with inverse fractionation up, fractionation going back down, that could do what it is that you're saying, and also what Vysotsky reported with the biological stuff increasing mass. This kind of thing, in my view, has a chance of accomplishing that, consistent with the picture.
Your model can explain no gamma ray.
Well, wait, the big issue with the gamma rays, the gigantic objection to a neutron transfer is that if you get to the other side, normally you decay by gamma rays. And if you've got an inverse fractionation, because it's coherent, if this runs as a coherent process, the coherent process is much faster than the incoherent process. So you can have the coherent process dominate by orders and orders of magnitude over the incoherent gamma decay for this kind of thing. So I think it can do it.
Thank you.
Great question. Thank you.
In those fracture experiments?
I'm sorry, what?
What was the neutron energy in those fracture experiments?
I'm trying to recall whether they were measured. I don't believe that there's a number. I'm not familiar with the number for the neutron energy. And I was actually interested. I was flipping through some papers to see if I could find a plot of the neutron spectrum, but I don't know that we've got a good number now. I certainly don't have a good number. But
they don't have because too low amount of neutrons does not make energy evaluation possible.
Oh, there's that. And in addition, it turns out that these big concrete thing actually has a non-trivial neutron reduction, scattering, thermalization reduction.
I was just thinking these fracture experiments and the Earth's crust differ in that they're under tremendous pressure. But none of your models taking that into account, and all the physics experiments are all usually like in vacuum chambers. Is it possible that physical constraints are somehow constraining what fission products could be made?
Your question is a good question. I'm approaching this very, very simply and easily. In order to transfer the energy, I want high frequency vibrations and I want large amplitude. Now, a fracture is an engine that generates large amplitude, high frequency vibrations near where the fracture occurs. Now, with respect to the selectivity of the final channel, that's determined sort of completely by what the frequency and what the amplitude is of these vibrations. So if they're maxed out, if they're highest frequency and highest amplitude, then I should max out the fission. And maybe I should go to the fission products, which require the maximum amount of energy input. While iron going to aluminum is that maximum. There isn't going to be anything obvious or clear with this kind of mechanism that's going to be higher up. Namely, all my spinning is like 55 and 1, 54 and 2, and so forth and so forth and so forth. So then when I get up here at 43 MeV with aluminum, that's the endpoint. So there's sort of a consistency with the selectivity and how hard you're hitting it. So in my view, these fractures with the initial fracture of lot of mass, high frequency, you're sort of doing it as much as you can possibly do, which is getting you to the end with the near equal mass daughters. So if it was a less enthusiastic fracture, maybe you get other products.
Well, but I'm not a physicist, but also it seems that aluminum and aluminum might have a smaller net radius than any of the other, 55 plus 1 and things like that.
Well, in a sense, and the hard thing about the nuclei is that they tend to be strongly coupled, so if you're trying to pull them apart, that's not an easy thing to do. So doing it sort of one bit at a time and getting it to be deformed and then more deformed.
Oh, no, yeah.
I have a question. Something unrelated, but it's geological, sort of. There's an issue over the ratio of deuterium to ordinary hydrogen in the oceans. We believe the oceans came from comets, and a lot of comets have a very different ratio of in fact, I think they have less deuterium, or rather more deuterium than our oceans do. So the question is, could the deuterium over the lifetime of the Earth have been modified to hydrogen or something else through some kind of LENR experiment? Not hydrogen, but helium. some LENR experiments over the millions of years of the Earth's ocean.
Again, in particular, in connection with the Mizuno experiment, he's got nickel and deuterium with very low pressure deuterium. So if this happened to be deuterium, and if we could figure out, I mean, sadly there's not very many good neutron states here except the ones that neutrons unbound. But if we could get this kind of thing going for deuterium, it would be a way of starting with deuterium and ending up with moving the neutrons to a neighboring nucleus, which would get you protons and you have fewer neutrons.
Has anyone looked at this problem of like the ocean's deuterium levels changing with time due to any LENR?
Not that I'm familiar with. I know. It's a good question. It would be fun to think about. And the first issue is, do you have a good way to study it? You've got ice cores going back to some number of...
Yes, and they have a lot of data like that, but it's varying with temperature, unfortunately. The deuterium, they actually use the deuterium concentration to measure the temperature of the ice at formation, I think. Somehow it changes, I'm not sure why.
Well, they have found samples of ancient ocean, like under the Chesapeake. They recently come across stuff that's 150 million years.
Well, there's a recent paper in Nature where they found that a very, very high pressure olivite mineral, which has water in it, led them to now believe that there may be an enormous amount of water trapped in the mantle. So what you want to do is do a measurement of the hydrogen isotopes in that, because that particular mineral probably goes back over 1.5 billion years. And that would in fact show exactly what you're saying now. You have now a marker that goes back and was deep within the mantle and has now come up through kimberlite, made it to the surface.
There's a complication because there's three kinds of comets. There's comets from the inner solar system that land here, and they have a certain ratio or mean value of deuterium to hydrogen. Then there's a Kuiper belt around the solar system, which has a different ratio. And there's the Oort cloud,
right,
which I think maybe they don't know what it has, but it probably has a different ratio too. So we don't know what percentages of these comets are hitting the Earth over time, so that complicates it. But it's definitely a suggestive opportunity for LENR, because rainstorms are going to cycle a certain amount of water through the land, every year.
To be studied afterwards.
Right.
Okay. Thank you very much for a very good presentation. This linking back to this fission mechanism. Is this really correlated to hydrogen embrittlement? We actually have very high pressure in the metal, and either by galvanic reactions taking place, or loading of the hydrogen in itself, and then creating these effects.
Hydrogen embrittlement is sort of this topic that's been studied in conventional electrochemistry and corrosion material science for a lot of years. And from my point of view, given once the density functional ideas came on board, they have effective tools to begin to study it, and they've been very successful in the literature. So I don't think anything like this is
bullshit. They don't work. In iron systems want to work in. The lattice is too compact. The tools break down in those systems. But what I really liked about your talk was you sort of connected this with your earlier talk, where you did the X-ray generation. Okay? Because when you stick mercury on a lot of metals, aluminum is one of the nastier ones, to generate atomically thin cracks at the frame level. So if you're vibrating this stuff or hitting it, you are essentially opening and closing cracks. Now it's going to etch the grain boundaries and copper. I don't know about the other elements. Aluminum and copper will react quite strongly at the boundaries. So you've actually got a fracture experiment in your vibration.
We'll try to follow up.
Peter, I have one question for you. Your model that you got for coherent fission, I'm thinking now about the Spey-Ward data where you look at the elemental distribution, and in particular, in the presence of a magnetic field, you end up with iron, you also end up with aluminum, starting with palladium. So would you see that you got an incomplete fissioning going on at a different energy, or do you in fact, those iron are now also spun up, and they then continue to go and then split down to aluminum?
My picture is associated with the hot spots. Normally, DD going to helium-4, fractionation energy goes into optical phonon modes, and the optical phonon modes, in a sense, are are almost immune against all this kind of stuff because they interact with protons and deuterons and so forth. If you've got acoustic phonon modes going, which I think is the original hotspots, then you've got the motion of the host nuclei. You've got palladium going on. So the palladium's doing the fractionating, which means the palladium's interacting with the energy. And then you can spin up the palladium, get it to fiss through this kind of mechanism. So I think in the hotspots, you've got acoustic mode energy production. And the fissing, the hotspots are hots because the fissing is highly exothermic. So locally, a huge amount of energy is going into acoustical modes, which is causing it to get hot and melting. And I think that's the origin of the elemental anomalies.
But you think it's the acoustic, not the optical modes that are spinning it up?
Yeah, the optical modes talk to the protons and deuterons. They don't talk to the
whole
host lattice very much. Anyway.
Simple question. If there is such splitting of fission of iron 56 into aluminum, we should see a large variation of the isotope concentration in natural abundance in the zone where they are rich in aluminum and the zone where they are rich in iron. So we should expect that there is more iron 57 and 54 in ratio with iron 56 in the region.
Which is the reason that every time I get one of these papers to review, I write back, can you do some isotopic studies and clarify this? No, I agree completely that to study this we need an isotopic concentration.
It should be very easy to check also without such experiment, but just looking in the zone of the near the earthquakes. If that area is correct, there should be a difference.
I agree. It may be aluminum is not the best thing to look for, but there are other examples of it which have other isotopic end products.
Sort of side comment about this ratio of the D2 and H2O in water. Way back, I can't remember, second full fusion meeting, Roghead and myself re-examined data from the Oklahoma natural reactor that was in Africa, and the French had great...
That's the uranium reactor?
Yeah. And we reinterpreted the data showing we thought that LENR processes caused some of the anomalies in data. That's in one of these proceedings. I can't remember the bloody details, but it's also interesting along the lines you're talking about.